Okay, Ken asked me to give this presentation, and in 20 minutes, I'll give you, I have a goal to give you an overview of my research activities and tell you about just one recent result. Okay, I've been working with robotic systems in the past. This was an unmanned flying vehicle at Honeywell this was 2002. We were the first ones to have, these are big machines. They were flying around, and they were used by soldiers. Okay, a lot of my activities are on automated driving, as you will see, autonomous driving. And more recently, I've been working, we got a project with Casironi on doing pediatric robotics. So I do work with robotic systems, and if you see all this, what they have in common, there is a human actuating or giving command to a system that moves in an environment which is perceived both by the system and the human. Okay, and in case of the cars, and I'll use the cars because that's the one I know the most, and I work all the time with it. There's a human that sends commands to a vehicle that moves an environment which is perceived by the human and the vehicle, and the loop is closed. And the main point of my research is forecast. So my lab focuses on the use of forecasting control, and I claim that we can drive pretty well because humans use forecasts. Okay, and actually I'm giving a strong statement. Probably the most interesting control problems left are on the one handling forecasts. Otherwise, they're either impossible or too easy. Okay, if you don't believe me, you probably have seen these examples, right? Color A is equal to color B. You agree? You don't agree? It is equal to color B. Your brain is forecasting 3D information, and because it's forecasting light, and it assumes that B is different from A. You don't believe? Okay, I'll show you that is true. It's amazing. When I saw this, I say, okay. And because there's a lot of stuff. Look at this. I'm just hiding this part so that you don't see. Right? I'm going to hide the part where it doesn't give you the 3D perspective. Come on. Yeah. Same color. So again, your brain colors are forecast, a lot of it. Okay, you have forecasting mechanisms. It's quite amazing. Okay, and this is probably one of the most interesting things I've been interested for the past 20 years, the use of forecasts, okay, in control, okay? Amazing, right? Doesn't look the same color, it is the same color. Okay, so how do we design a control that forecasts the vehicle dynamics, the environment dynamics, and the human behavior, so that we make the whole driving experience safer, or robotics experience safer if you change your systems there, and eventually you can make it autonomously. So again, two goals: overview of my activities because this is a Cpar seminar, the human-vehicle interaction, and just one research result. I've chosen analog optimization as an example of picking something that is a bit different what is out there. Okay, being futuristic with what we should do at university, looking at maybe 50 years ahead. So what do you need forecast? Because your system has dynamics, has inertia, and you want to follow the green line to avoid the red regions, right? And in your forecast, your model, you have a control action, but you have things that are uncertain, like the human action on the system and the environment. Okay? By forecasting, you anticipate and you coordinate all your control actions. So what are the challenges? Going from this simple idea of using a forecast in your control to making it work. Where do I start from? 3 questions. What is a good model abstractions? Do I really need forecast? What is the value of uncertain predictions? Do I need to use forecasting control? And how do I make it work? Okay? Where do I start from? Do I really need it? How do I make it work? So I'm going to use this part here, a good model abstraction, to tell you a little bit about our research activities, and also to as a message to the young graduate student to know, tell them to know a bit, study the system before trying to control it. Okay, and predictive control design, I'll tell you a little bit one research topic in here. So if you look at the car, the human moves the vehicle. Today, the way we actuate the car is sending a signal to the low-level control systems, right? When you change your steering angle, you push the brake pedals, you're really referencing into a low-level control system. For instance, if you push the brake pedal, you know that you're sending a signal to the PWM. You're sending a signal to an electronic control unit, which changes the pressure inside the braking pads, and it's a PWM signal. And really, what you really want is not what you get. So, okay, this is experiments that we do, but so there is uncertainty in the low-level actuation. And by the way, if you take a modern car, there are what you can do. You can brake all four wheels. You actuate the engine torque, but you can also distribute the torque in front and the rear. And you can, of course, control steering as well as them. This is a Hyundai Genesis 2015. It has all these form of actuations. Okay? Interesting control problem there. Now that you have sent signal to the vehicle moves in the environment. And so there are two types of interactions. So the vehicle is a box. The lower side, it interacts with the road, right, with the asphalt. And around you with obstacles. So tire is the reason why things move. And these are tough objects. These are viscoelastic materials. So there are entire conference on tires. This is the force. What I've depicted here, the force to the tire is a function of what is called tire slip. This is the normal difference between the vehicle speed and the wheel speed. And it comes from finite element models of the tire deforming under the effect of accelerations. And so, a lot of people doing vehicle dynamics use this type of nonlinear models. Okay, if you think about if you accelerate, your force is going to increase up to a point where the tire slips, and actually you get less traction. And the same happens with braking. Okay, the second interaction is with and this type of shapes change as a function of your surface. The second interaction is with world around you. This is our car driving downtown Berkeley, measured by LiDAR, camera, all type of sensor radars. There's a lot of work that you can imagine goes in here. Robotics know much better than me on SLAM, classification, sensor fusions, all the algorithms that you need to properly localize the vehicles, your position, and the vehicles around you. Okay, and once you have the car moves in the environments. This environment is perceived both by the car and the human, okay? And this is where the neuroscience community here have been focusing for many, many years. What has changed in the past year is really that this is a Nobel Prize, Eric Kahn is a Nobel Prize neuroscience, that they have embraced this idea that we have a simulator, we have a forecast in our brain, okay? And we have a model that makes forecasts. And if you use this concept, then you explain why we need a traction control and anti-lock braking system. Your mental model in the brain is a linear model. A lot of our stuff in the brain for mechanical systems is identifying simple linear or piecewise linear models. So we have a simple linear model, which works okay in this region, but when your wheels are slipping, whether in acceleration or in braking, you need a control that takes over because there is a model difference. So this is why you need a traction control here, and it's called anti-lock braking systems here. Those are production controllers, right, that help you in this region. So this is an example. If you see here an expert driver, okay, you would have seen the expert driver doing this curve at high speed and counter-steering for doing this curve. Okay, so because the expert driver has the nonlinear model in his brain of the tire characteristics, he knows that he has to turn in the opposite direction of the curve to get maximum lateral force. Okay, here's the same condition by normal drivers at lower speed but was slippery. Okay, and you see that they are not able to stabilize the vehicle. Okay, and the point is that there is really today we have no way of anticipating or forecasting what the driver is going to do in these conditions. There is no driver model in these scenarios, and you can imagine it's extremely useful if you want to help the driver, assist the driver in driving safer. Okay, so what I've been doing a lot of in our lab is to focus on real-time data-driven human driver models, and the reason is to have better human-vehicle interaction and also fast training of less skilled humans. Imagine if I want to teach people how to do complicated parking. Okay, can I design algorithms to teach people to do parking? So what are the challenges for what are the challenges compared to the neuroscience world? The neuroscience world, you have seen, they have this type of experiments. It's a very simple task, move your mass from A to B. They're usually interested in a mean behavioral population, and they're very controlled experiments. Our stuff is challenging because we actually are looking at each individual, and we want to have personalized model. I want to distinguish between Ruzhna and myself. This is a very complicated task.
Much more aggressive.
I know. And there are a lot of uncontrolled external factors. So a lot of work. This is, actually this is an old slide with Ruzhna, Victor, Ram, who's now in Michigan, Stephanie, and there are many more people since we started. Actually, this is not really 2009. This is more like 2005. We came here. And it does depend on which type of scenarios are you interested in. Are you interested in exploring the nonlinearities of the tires, right? Vehicle dynamics and no obstacles. Are you interested in parking? That's a problem where you have static obstacles and you have non-alarmic constraints, but the tires really work in the linear region. Are you doing highway driving, where you have few dynamic obstacles, a bicycle model works well, or you're doing city driving? Okay, so if you go back to this, an overview, this was our test where we ask expert drivers. Oh, I'm sorry. You will see this car doing what this car is going to do. It's going to do a drift and 180-degree maneuver. Okay. This is in Michigan or snow, and only expert drivers can do this. And basically what they do, they first destabilize the vehicle, they go in high drift condition, and then they stabilize it back and rotate. And so we were asking, can I learn from the expert driver and can I teach? It was an interesting research from Teresa that is graduating now in a few weeks. And actually, a switched piecewise affine, a two modes piecewise affine mode, stabilization, destabilizing versus stabilizing works extremely well. So well that actually we can use the same model identified from the driver to run autonomously the car. So you would see the car doing autonomous drift and 180-degree maneuvers from this controller learned from the driver. The parking is actually something that humans are really bad at, okay? Especially if things are, this is the same scenario. The video to the left, the guy destroying the car, and this is an optimization. And by the way, the reason I show this is more for the faculty. Ask your student to solve this problem. It is a very simple problem which is extremely difficult, okay? You won't, and especially if you give them constraints as to run on a real-time electronic control unit. And we have posted some GitHub simple code to solve this type of problem. Highway driving, this was some of our most recent research where we ask people to drive cars and we record external data, the cars in front of you, the cars around you. And so we learn the driver behavior based on this historical data. We identify a hidden Markov model, a Markov chain from the transition between the control strategies. And the message here is that we went, 5 years ago, we proposed this personalized driving. Basically, the car drives the way you used to drive if it is safe to do. And it works pretty well. Okay, so a model here, you can see two examples here. For the same rate, this is a car keeping the lane and having, a distracted driver and doing what is called lane departure. Basically, you are exiting your lane. And with this type of models, we can forecast 2 seconds. Okay, here is the 1.8. So 0.2 seconds earlier, the lane departure, which is 60 miles an hour is it's a lot compared to production systems. Okay, the other thing that we can do, we can actually show, according to two metrics, the quality of the personalized model versus an average model. So the fact that this is lower means that the personalized model, it captures better your driving style. Okay, so basically we can, next time you drive, we'll record your data, we'll make a personalized model, and we'll use that model to make your car safer when you drive, or you make that model to drive the vehicle in autonomous mode when that will be possible. Okay, so this was a big picture of a little bit of our lab activities. Just 5 minutes on going back to useful model abstractions. We have a nonlinear dynamical systems. We have coming from Euler equation of motion, static time nonlinearity, inequality constraints on your safety region, and certain forecasts coming from drivers. Okay. Last 5 minutes is what is about control design. How do I make this work? How do I use this forecast in real time to control the system? Well, if you look at the challenges, this has to run on an embedded platform. Okay, this is one of the biggest challenges in my lab. Basic setup, repeatedly solving a finite time optimal control problem where new forecasts and new states come and are updated each time step. You're looking for, an horizon is n, you're looking for a set of n feedback policy that minimize the costs subject to your system dynamics and constraints on input states for all uncertain behavior, okay? This is what the word of MPC, or Predictive Control Community, does, okay? And there is really 2 aspects to it. How do I compute this? And the second one, if I'm not able to compute exactly the same problem, how do I compute a simpler problem that fits an embedded platform? Okay? 5 minutes. How do I compute that? You have 2 options. One is do it offline. Okay? There's a lot of work offline, and then online is just a lookup table. So pi, your feedback policy is a piecewise constant policy. Okay? Dynamic programming to compute this pi is one option. We teach this in class. Basic rule, an n greater than 5 is impossible. You cannot grid really in 5 dimensions. Okay? The second option instead is, the 2 extreme, is online. So offline, you just set up your problem. These are my costs, these are constraints, and then in real time, you solve an optimization problem. And nonlinear predictive control is one choice. Okay? The basic message here, what is the basic rule, is that you want to avoid homemade solvers. Do use solvers from the operation research world because they've spent years on these things. Okay? So what has changed in the past 15 years? I think I gave this presentation a few months ago. I was thinking about it. And really there is a couple of things. First of all, excellent open source convex and non-convex softwares are available. So you should really use them. IPOpt is one of them, all things out there. The other one, if you see how people in robotics do obstacle avoidance, they don't solve a mixed integer problem, right? There's a lot of sampling, particle-based filter. And there's only one reason, that these solvers in the operation research world do not allow what is called, here I call it in-place problem modification. If you solve a problem with horizon n, you want to solve a problem for n plus 1, you have to resolve the problem again. Okay? This is changing. If you take Julia from MIT, allows for in-problem, you can use all the information you solved before, all the algebra for solving n plus 1. And this is why actually these sample-based methods work better, because for whatever information you have till now, you add and you can solve faster. Okay? But after, I think once operation research solves this in-place problem modification, then all this random stuff will go away. This is my view of the world. Biased view, as it's written up there. And there's another thing that has changed that I probably skipped because there is no time. But I think the most important, I was reading this book. It was interesting. Yeah, this is the Nobel Prize in economics, right? I don't know if you've read this book, Think Faster, Think Slow. He has the first chapter, starts saying that the brain has 2 systems. System 1 and System 2. System 1 operates automatically and quickly, and System 2 allocates attention for, it does complex computation. It does this option, 3 plus 3, you don't compute it, 250 times 120, you compute it, you haven't stored it. And I think they kind of got it, you see, it's exactly what I'm talking about before, okay? So rather than, I'm not sure I would really differentiate, I don't want to say they got it right, they got it wrong, but it's really the same system. One is pre-computing and storing, the other one decides to do things in real time. Okay? And this was what my PhD thesis was about. I was looking for a special class of real-time optimization problem that had a simple feedback policy that could be pre-computed. Okay? This was switch linear systems, polyhedra, and piecewise quadratic or linear cost. And this policy looks like a complicated thing. It's piecewise affine, it's affine pieces on regions, on objects, and these objects have strange shapes, but there is software to compute this. And if you buy if you buy a Mercedes-Benz, this adaptive cruise control, you see this lookup table here? The adaptive cruise control is this pre-computed feedback policy with my tools. Engine control today in a lot of companies is done in these ways. Okay, this is a product that I've worked with Honeywell on-ramp while I was at Honeywell. Okay, last message. One last result, okay, from my lab. Oh, by the way, in terms of autonomous driving, we have an open source architecture. If you want to work on autonomous drive, you can download our stuff, and you can put your best estimators, your best controller, your best path planning algorithm, and you can pull data from downtown Berkeley and simulate it. So everything is in ROS, Python, C++, so you're welcome to use this and download this. So what is the last result I want to show you? At the end, you have to solve an optimization problem, right? And I'm interested in this predictive control, you have to solve this object, which is transformed into an optimization problem, where the state or the forecast enter the cost at the right and the constraints. Okay? This is really the OR word here. And solvers are getting faster, but CPU is not. Okay? So the clock here, this is the clock of CPU, CPU clock over the past years. You see it's stuck at, this is 4 gigahertz. Okay? So they just put multiple CPU, but over the past 10 years, they really can get it because of heat dissipation. You cannot get faster. And by the way, in the automotive world, this was a shock to learn that. They went now in the new ECUs that they have multiple cores, they turn the multiple cores off. Because actually, sometimes it generates conflict, and the task becomes slower than what they really need. Okay, so short story, we've been looking at ways of speeding up computation of solvers, and if you are interested, and we went back to analog optimization, and this board, it's an analog board. It solves a QP. Actually, the biggest part is an Arduino to connect it with the digital one, but it solves a QP. It solves this QP here. Solves a QP. I'll save you from the theory and the Lyapunov stuff and so on. It's all nice, but the most important thing is it works. This solves the QP. How could I go through this in 30 minutes? I don't know. Here it is. QP with 21 variables and any QP and 15 constraints. Okay, 14 constraints plus 10 equality constraints, and it's faster than any digital system out there. Okay, so we went back. It's called analog optimization. It is the equilibrium point of an analog circuit. Is the solution of a QP. Okay, it's an old idea. It goes back to the 50s. There's somebody here, Chua, called at Berkeley, was doing this. Our circuit is much simpler and faster than what's published out there. These are the results. It doesn't need, by the way, it doesn't need any operating system. It doesn't need Linux. You don't need to update from the cloud. That's it. Thank you. If you want to know more about this, there was a seminar today from my PhD student, and there is a lot of information on the web. Thank you.
Thank you. I'm sorry we have to push you into such time constraints.
I was.
Tommy, do you want to set up the computer while we take a quick question? Sorry, any questions from the audience? Okay, I'm afraid if I ask you, it's gonna get too long. But we can follow up later. I think I didn't know you're working on actual analog hardware to solve these problems. I mean, the key in MPC is that you have to be recomputing during execution, right?
Yes.
Okay, and so it seems as though there's also some verification or performance guarantees you need to have, right, as well, because you can't. There's some limit to how much time you have to compute, so everything has to converge, and you have to be guaranteed. Okay, good.
Very interesting question.
Yes.
This is one of the biggest problems of our community. You can guarantee convergence in a given time for these iterative algorithms. Okay?
You cannot.
You cannot.
Okay.
But the good news is that nobody can. Okay. Even any other sampling-based method are not guaranteed to.
Yes.
Okay. So.
All right. Terrific. Thank you. And our next speaker, fantastic. I'm so glad he's here. Tom Mazuka is Professor Tamazuka is a distinguished faculty in mechanical engineering. He's actually been on leave, spending a fair amount of time in Singapore. So we're extremely happy to have caught him here for a visit back to Berkeley.
Okay, thank
Professor
you. So
Tamazuka?
it's another robot-human collaboration, but it's in factory environment. And my lab, called Mechanical Systems Control Lab, is doing very much deep into industrial robot control. We do research for speed, accuracy, vibration, suppression, intelligence, safety, etc. And one of the themes is a human-robot collaboration. And so in this talk, I'll cover two topics. One is human-robot collaboration in peg hole insertion. And another one is safety, when the robot and human are working together. So human-robot collaboration in peg hole insertion, there are several keywords like teach through teaching and learning skills from human and so forth. Two guys, Tae Tang, Sen Chen Lin, they are the researchers working on this topic. It's a robot assembly. It's all over the place because it's manufacturing requires lots of assembly. And if you look at tendency becoming smaller dimension, tighter tolerance. Tighter tolerance is very important aspect. And also short production life cycle, so it has to be flexible. So human-robot collaboration may take place. Robot is very precise. Human is lots of experience, and he finds how to do things well. So we take advantage. And this is not a classic problem. My advisor, Dan Whitney, that's almost more than 40 years ago. So he was working on this type of things. And I didn't talk with him at that time, but now if you look at the traditional approach, maybe for the approaching thing, you use teaching pendant to bring the robot peg close to the hole. And then the teaching pendant, you have to be aligned fairly carefully, because if you can come close, you don't have to do tilt compensation. But it's tough work. Then traditionally, it was done force damping control. And I think if the tolerance is not that great, maybe this is good enough. But we would like to do more flexible way. By the way, teaching pendant is one of the most consuming part of the robot operation. People would like to stay away from teaching pendant. So we do read through teaching and then alignment scale from human, and this we learn from human. First, this part. Essentially, this is read through teaching. Instead of moving the robot by pendant, in this case, Tae is moving the robot towards the hole. So this is obviously something force control is going on, because robot moves in the direction he is pushing. Now, the force control, it's easy to bring somewhere in the vicinity, but if you try to do everything by nicely hold and peg lined up and so forth, it requires lots of effort. And also for safety reason, you don't want to increase the bandwidth of control loop too much, because human and robot are so close. So it's fairly easy to bring the robot close to the hole, but mostly not likely already hole and peg lining up. And what then will happen is you can come close to something called so-called 3-point touching. Okay, if you are very close, okay, the robot may be already touching the hole at 2 points. But if it has got angle, there are 3 points. Okay, so most of the previous research assumes that you can come to the 2-point contact, and then insertion game started. But it's more 3 points. So this is how typically human does. Find hole, then correct. Okay, so my student essentially figured out if you come to 3-hole touching, you can measure the by force sensor force in XYZ direction, in the force sensor direction. And based on that, make prediction of what is the tilt angle. Okay, so if you plot tilt angle versus this is estimate. essentially force data is utilized, how you don't have to worry at this stage. But you plug in formula, and you can expect what will be the estimated angle. And it's very come close to the 45-degree line. So make use of this one. Then essentially robot come to the 3-point contact, then easily come the hole and peg almost lined up, come to this stage easy. And once you do that, you have now insertion phase. And insertion phase, what human people normally do is essentially if you look at the peg, you can move peg in certain direction. And there is also the reaction force from the hole. So those two should be nicely correlated. So the human does very good game in here. So we try to learn what human is doing here. And once such learning is completed, essentially this part is gone. And robot can start doing all the tasks himself. Okay, so essentially force and velocity in which direction this peg should be moved are the two key variables. Certainly the relationship is not linear. It's quite nonlinear. So objective is to produce a very nice mapping between these force and velocity, the information, and essentially use regression model approach such that estimated velocity, real velocity may be close to each other. This one essentially fits the experimental data, what human is doing. So you get lots of data, and then what the process is, first, which as he moves towards a hole, there may be some section you'd like to throw away because it's not quite relevant to the insertion part. And so there's some suppose vector machine pick up the component relevant to the insertion. Then lots of data collected. And as human perform, each time he's doing a little bit different speed. And that is normalized by the idea of time warping. And then the regression model can generate fairly close to what human does. Okay. So the regression model, the Gaussian mixture regression model, essentially this is experimental data relating force versus velocity. In a simple case, both quantity is 1, but in reality, it has got 6 dimensions for each force and velocity. And then essentially this kind of relationship is represented in terms of some probability like this density function, so Gaussian model. And identifying this, you can do the job. Okay. And once you run the module, force sensor pick up force, and based on that, this module can figure out in which direction the velocity should be selected. And once you do that, you use some inverse Jacobian to convert the XY, the task space information to the robot joint information. Then standard robot control follows. Now this whole package is essentially going through. This is first read through teaching part. Come to a reasonable 3-point contact. Then angle is estimated from force data. It becomes 2 or 3 degree error. From that point on, insertion becomes easy. Then based on that learned model, this insertion be achieved. Okay? So that's one story. Another story is coming from Chanliu Liu, and she's working on algorithmic safety measure for intelligent industrial co-robot. Now people figured out that future factory should have both robot and human working together, taking advantage of the strengths of each, but there are lots of interesting issues involved. The figure is from RFP for the National Robotics Initiative. And obviously, the advantage of robot and human, we try to make synergistic use of 2 things. And then future robot factory might look even some already now, factories start looking that robot and human collaborating in various ways, including the robot cart moving the part from one station to another, while human inspector walking around. So lots of technical challenge. Okay, if in the environment, if you would like to ensure the safe operation, sensor perception, how the human motion may be recognized by robot, human recognizing robot, and so forth. But the key issue is safety. So we try to ensure safety. And there are several protection levels. The first is essentially recognize each other, that we are close to each other. People may not know that robot is coming close. But essentially, we try to give responsibility to robot. Robot find human in the vicinity. But for doing the sense and perception, cognition, motion planning, and second stage of protection is unfortunately some contact take place. Such contact has to be immediately sensed. And in some cases, if you can put soft mechanism, either joint may be a little bit elastic, or robot is wearing some jacket, that might be another level of the protection. Industry people essentially came up with very simple idea. This is Fanuc green robot, essentially intended for human-robot collaboration. What they did was to control the impact. They decide to move fairly at the conservative speed. Impact, essentially momentum is m times mass times velocity. So if you can reduce one, in this case reducing velocity, so make the momentum go down. So move slowly, and also is surrounded by the scanner sensor to find the human. And then if something touching takes place, they have got a very sensitive force sensor in the base of the robot, so that immediately detect that something happening. And if it's unscheduled, unplanned collision, touching something, robot immediately stops. So that's something like human does. And in Chandu's case, she wants to do some more from motion planning point of view. Given data, she can make a situation that the robot predicts that the collision may be taking place. Then under that scenario, what kind of motion planning, actually trajectory planning has to be done in real time. Okay, so to do that, essentially there is some hard constraint. Try not to collide each other. In the human and human interaction, you might call it something like social norm. You don't want to hit anybody. But even you try to avoid hitting anybody, there is some uncertainty coming, whether this guy is coming to this way or that way and so forth. There is certain uncertainties which has to be taken care of. If in that situation, the choice that you can do may be further limited to deal with that kind of uncertainties. And so pretty much this type of goal can be achieved by certain control theoretic algorithm. From control point of view, she utilized multi-agent framework. So each human and each robot is given some dynamics, some sensing mechanism, and some control actuation mechanism. And in this story, essentially this first agent is human, and essentially first agent is robot, and the rest is other moving object. So we think about what kind of control algorithm has to be done by the first agent, i.e. robot. So essentially, this robot sends all the information, and based on that, robot controller decides the proper action. Now, essentially, it's an optimal control problem because robot is there to accomplish certain task. So what will be the control strategy to accomplish that task? And if you can forget about, for now, bumping human and so forth, it's just a standard optimal control problem. You can use LQR or something to reach there. Okay? But then you have to think about that if something is there, you have to avoid. Okay. Now, if you try to avoid the certain obstacle by working on this set, okay, there is human, and so forth. It turns out that the space you can play with is not convex. It's a rather convex optimization problem. So instead of doing that, what Chan-Liu does is try to find the control UR such that she can be safe. Now, how does she do? Okay, so suppose you have to be in this blue set in the space. This is robot. X1 is robot position. X2 is anything else, human, and so forth. Here, it's safe. No collision will take place. But if X2 is going to move down here, robot should be somewhere around here not to bump. Then it has to be moved up somewhere around here. Okay, so how can we make sure that this will happen automatically? And for doing that, instead of worrying about this excess directly, she looked into what she calls safety index. In state space, she makes a function phi, which is a function of state. Function has to obviously satisfy certain constraint. If phi is positive, phi dot is always negative. And she can cook up that kind of function. And if the phi is behaving always like that, phi will go below what she calls level set. And if going to the level set, it's guaranteed to be safe. So instead of X staying XS, she would like to make sure that actual use robot applies to belongs to this set. Okay? So without essentially first worrying about what the robot obstacle is, we just first solve this optimization problem. That essentially decide so-called efficiency controller. Efficiency controller simply achieves the original task objective. Then looking into where the danger is. Instead of searching X space, she goes into URS and selects proper UR. So conceptually, that part is do, but something that happens is if UR is not belonging to the safe control set, essentially find a point where it has got minimum distance and do this. Now, something dealing with uncertainties, the robot is again here, X1, and another guy, group, may be moving down here, but not quite exactly to this point. There's some uncertainty involved. But then in that case, pictorially XS, where X can be very further narrowed down. Essentially, she figures out what will be the safe set control for each of these X2, and she finds a sort of set, whichever the X2 end up, she can still ensure safety. And she simulated this idea, some mobile robot, planar robots, 3 degrees of freedom, 6 degrees of some robot, and circular obstacle, and so forth. And space, 2-dimensional simulation, 3-dimensional simulation. It's kind of interesting simulation. So this is, the first scenario is mobile robot. Mobile robot moving around and helping human. Human has got some task to do in the right circle. Mobile robot has to go red circle and accomplish task. And so mobile robot can go there as long as it's not conflicting with human. But when this blue guy, human, come close, it stay away from the human, this robot. This is for the planar robot arm and human working together. This is more co-robot, typical co-robot scenario. Robot is next to the human. Now, this is the human target point. Human has not come to this yet, so robot is doing his job. But when the human is coming in, okay, this is human, robot stay away from human. and still accomplish task while not hitting human. This is 3D simulation. In this case, human is represented by point cloud. So the robot is supposed to pick up this yellow thing, or this yellow. The human come close, robot stay away, and not to hit human. This is more typical. We have got this in the lab, M16 robot arm. And this is a robot task. If nothing, no obstacle is there, when the humans start moving in, instead of precisely following this path, robots start backing away from the original trajectory. Now, for doing all of this, okay, for safety calculation, essentially this is simulation use the Apple computer, the MATLAB on a MacBook 2.73 gigahertz. So each cycle to figure out that it was only this much millisecond, but good portion of the millisecond was used for figuring out the minimum distance between robot and human. So if you attach some sensor to the robot, the end effector, and directly looking into the space, you really don't have to do this part. So everything is very quick. And last simulation is so-called human in the loop simulation, because instead of jump into experiment directly, so Tay is looking into Kinect sensor and also screen. And as he moves towards screen, robot is trying to avoid him. Robot is supposed to move back and forth on this red line. So this is Tay on the screen. This is real Tay. Okay. So this kind of simulation. Next level is to experiment. Oops. Okay, conclusion. Okay, so robots are more and more penetrating to various industry applications, and it's generating lots of opportunity for the interesting robot-human interaction. Okay. By the way, some of the work we are showing about robot-human interaction here is not really limited to factory automation, but can be used for automated driving and maybe even some medical robot and so forth. Okay, thank you very much.
Questions? Quick one for you, Tommy. Have you started work on combining the two ideas, namely that the learning and the safety? In other words, it seems as though one idea could be that you could over time learn to predict the motion of the humans that might come into the environment, so that you could predict what they're doing, and that way allow the robot to move faster to reduce the safety margin. Or vice versa, I think it's kind of interesting that you could imagine the human getting a warning in some way that the robot is moving in their space, and so it would warn the human to move back. Mm-hmm. And so you could learn on both sides. I'm just curious if you... Mm-hmm.
Yeah, I think that the basic one, the second part, we treated human as a very absent-minded agent. Okay, so that from the safety point of view, that might be good. Yeah. But I think there is an opportunity that more the other way around. And also, the humans' intention, teaching humans' intention, learning that humans' intention, we have not quite done that part yet. So we will be spending more effort in that direction. Okay.
Very good, because that's related to somewhat to Anka Jargan's work. She's the new professor here. Okay, great. We should also talk a little bit about the segmentation project, because that's related to some work we've been working on as well. Okay, terrific. Thank you so much.
Okay, thank you.